In the last video, we visualized an ethane molecule with a Newman projection. What I want to do in this video is show that you can really visualize longer chains, or even, we'll see in future videos, even cyclical ring-based carbon molecules with Newman projections as well. And I guess the next most complex molecule to study would be butane. Butane. We could do propane, but butane will be interesting. This was ethane right here. Butane will have 4 carbons. And if I were to draw it in kind of a ball and as a ball and stick model, it would look like something like this. So this would be 1 carbon right there. Then you would have another carbon right over there. Then another carbon right over there. And then you would have your 4th carbon. And then your hydrogens, you would have a hydrogen coming out like this, like that, and then up like that. This guy would have 2 hydrogens that would stick out like that. This guy would have 2 hydrogens that stick out like that. And then finally, this guy will also have 3 hydrogens. It's a CH3, just like that. Now, if we try to draw a Newman projection here, it's like, well, what do you consider the front or the back carbon and all of that? And you actually can pick. And what's interesting in a butane molecule is if you pick this guy, so this is the 1, 2, 3, 4 carbons. If you pick the 2 carbon as our front and our 3 carbon as our back, and then we view this carbon, this CH3, as kind of one of the add-ons onto that carbon, you can then do a Newman projection. So let's try to do this. So this will be the front one. So we'll put this carbon in the front, and we'll put this carbon over here. We'll put this carbon over here in the back. And before I even draw the Newman projection, let me redraw this. But I'm just going to draw this instead of with the hydrogens, the bonds explicitly defined. I'm just going to call this a CH3. So let me redraw this. So I'll do this in orange. So you have this carbon. I'll do this kind of as a modified ball and stick. So that carbon, it has a hydrogen. It has that hydrogen and that hydrogen. And instead of drawing this out, I'm going to just draw this whole thing right here, and I'll do it in magenta. I'm going to draw this whole thing as just a CH3. So I'm going to draw this whole thing as just a CH3. So I'll draw it really big because it's not just 1 atom, it's 4 atoms. So this is our CH3. And well, to do ball and stick, everything really should be a ball. So I'll draw a ball there, ball there. So that's our carbon number 2. And then it has this bond. It has this bond over here to this carbon number 3, which when we do our Newman projection, we'll put in the back. So our carbon number 3 is like that. And then the carbon number 3, it has 2 hydrogens, and then it has this. You can kind of view it as this methyl group attached to it if you want. It has this CH3 attached to it right there. So I'll do the CH3, I'll do it in this blue color. And so we could draw it like this. So the CH3 is coming off. So I'll draw it really big because it's not just 1 atom. So it's a CH3. And then you have your 2 hydrogens. And then, sorry, you have your 2 hydrogens down here. So let me be very clear here. So let me, this hydrogen, that's that hydrogen and that hydrogen. This thing here is that thing there. That big ball right there is this whole ball. And then let me find I'll do green. This hydrogen and this hydrogen is this hydrogen and this hydrogen. And when you look at it this way, now you say, oh, now I can see how I would draw a Newman projection. I put this in the front, that in the back. I treat this whole part of the molecule as just a group, if you will. It is a group. So let's do the Newman projection here, and then we can think about where it's most stable. So the way I've drawn it right here, so you have your I'll do this as the front. This carbon 2 is going to be the front molecule. So you have this CH3 group going down, and then you have these 2 hydrogens. You have these 2 hydrogens, hydrogen and hydrogen. That's the front. And in the back, you have this blue one. You can imagine in the front, if we want to, maybe I'll do a little small orange thing to show this is the orange carbon. And then the blue carbon is going to be in the back. The blue carbon is in the back. I'll draw it like this. So that's my blue carbon. And the way we've done it here, we have a CH3 pointing straight up. And then we have our 2 hydrogens. We have our 2 2 hydrogens. Now, just like we talked about in the first video on Newman projections, all of these groups have, these hydrogens have electron clouds around them. This whole CH3 group has a larger electron cloud around it. It's a carbon atom plus hydrogens. They all want to get away from each other. And the CH3 is even a bigger molecule. So to some degree, it's going to play a bigger role in whether something is a higher or lower potential energy, or whether it's wound or not. So I guess the most obvious, or maybe it's not obvious, but the CH3 group, since they have the biggest electron crowd, they're kind of crowding the molecule. This CH3 group and this CH3 group, they're going to want to get as far away from each other as possible. So the way we did this, it looks kind of like our staggered conformation, but when we're dealing it with actual methyl groups that are separated as far as they can from each other, we call this the anti-conformation. We call this the anti-conformation right here. Anti-conformation. And if we think about dihedral angles between the two methyl groups, the dihedral angle here is 180 degrees. 180 degrees dihedral angle. And this is the lowest potential energy, or the most stable. And that confuses you when I talk about lowest potential energy. Just think about it. A rock on the ground has a lower potential energy than a rock that is 50 feet in the air. A rock on the ground is also more stable. It's less likely to do something. Something 50 feet in the air, maybe if you nudge it a little bit, it'll fall off the cliff or wherever it is. Or maybe it's already falling. Who knows? It's going to move when you have higher potential energy, or it takes very little for it to release energy. But when you have lower potential energy, you're more stable. So this is the most stable conformation. Now, what are the other situations you could do here? Well, you could keep rotating these. Let's say you rotated the back carbon around clockwise. What are the other conformations we could get? And so let me just draw the front portion right here. So you have your CH3. You have your CH3, and then you have your 2 hydrogens, hydrogen and hydrogen. And let me copy and paste this. So there's 2 other there's everything in between, but these are the ones that are interesting. Control copy, and then let me copy it, copy and then paste. So I'll actually draw 3 of these. So then you have that, and then let me paste it one more time. And then you have that. So these, obviously, this would be the front carbon in every situation. If I want, I could make it a little orange dot to show that that's the front carbon. And then let me draw the back carbon. I should have copied and pasted this as well. So you have your back carbon in every situation. Now, if we were to rotate this character by 60 degrees, if we were to rotate the back by 60 degrees, what would it look like? Well, then we would have this hydrogen would move up there. So then you would have this hydrogen. Actually, if we were to move it by 120 degrees, I should say. This would be 60 and then another 120 degrees. So this hydrogen would go up there. This hydrogen would go up there. This methyl group would now be over here. And then this hydrogen would go over here. So we've just rotated the whole thing by 120 degrees. We've rotated it by 120 degrees. Now this conformation, this was called the anti-conformation. It's the most stable because the methyl groups are as far away from each other as possible. This right here is called the Gauss Confirmation. The Gauss Confirmation. Let me do this in a different. This is the Gauss Confirmation. And you can view this as the second most stable. At least the methyls are staggered. They're not directly behind each other. So here the methyls are as far apart from each other as possible. If you look at the ball and stick model, I actually drew it in that conformation right here. They're as far apart from each other. If you were to flip this molecule, if you were to flip it, this methyl would get closer to this methyl, and their electron clouds would start to crowd each other. So in this situation, this is most stable. If you rotate a little bit, they'll get a little bit closer, but they'll still be staggered. You get the Gauss Confirmation. Now, if we rotate this, if we rotate the back guy now 60 degrees clockwise. So if we rotate it just 60 degrees clockwise, what's going to happen? What's going to happen? Well, then you're going to have an eclipsed conformation where the carbons are where the methyl groups are directly behind each other. And that's going to be your least stable situation. right? So you would have this guy, and I'll draw it slightly. So you'd have this guy, CH3 there, and then you would have your hydrogens that are right behind each other. So a hydrogen and a hydrogen. So in this situation where eclipsed, this is the least stable, and also the most potential energy. And then if we were to go another 60 degrees from this, then we go to another Gauss conformation. If you rotate this another 60 degrees, then you'd have a CH3 here, and then you would have this hydrogen would be up here, and then this hydrogen here. So this is staggered. The methyl groups are, at least they're not directly behind each other, but they're not as far as they could be if we were to rotate another 120 degrees and get to the anti-conformation. So this one right here is also a Gauss conformation. So hopefully you understand now that if you just have to pick two carbons, and then you can, if there's kind of big things attached to each of those carbons, you can just represent them as groups. And when you do that, you can really use a Newman projection for any part of a molecule. And when you do that, you can start to think about how it can rotate and what parts or what versions of it will be more or less stable.